Mach 3.2 flight generates skin temperatures exceeding 800 degrees Fahrenheit, instantly melting conventional aluminum airframes. Aluminum alloys fail completely above 350 degrees. The SR-71 Blackbird required a material that retains structural integrity and stiffness under extreme thermal load, leading directly to titanium. Specifically, 93% of the SR-71 structure utilized titanium alloys, primarily to manage thermal expansion and kinetic heating effects that would destroy conventional airframes. This necessity drove the largest single procurement of titanium in history up to that point. The material had to withstand prolonged exposure to high heat without suffering creep deformation or loss of tensile strength, a requirement far exceeding commercial aviation standards. This thermal requirement dictated the entire fabrication process and supply chain strategy. The primary alloy selected was Ti13V11Cr3Al, a metastable beta alloy known for its exceptional strength-to-weight ratio and high-temperature performance. This specific composition offered superior ductility compared to alpha-beta alloys, which was critical for forming complex structural components. However, the alloy presented significant metallurgical challenges. It was highly susceptible to hydrogen embrittlement, requiring extremely strict control over atmospheric contamination during processing. Furthermore, the alloy exhibited a tendency toward hot cracking during welding and required precise heat treatment schedules to achieve the desired mechanical properties, often involving solution treating followed by aging. Failure to adhere to these narrow parameters resulted in immediate material rejection. Working with titanium alloys at this scale was a fabrication nightmare. Titanium reacts readily with oxygen and nitrogen at elevated temperatures, forming a brittle surface layer known as alpha case. This contamination severely reduces fatigue life and structural integrity. To mitigate this, all welding and hot forming operations had to be conducted in inert gas environments, typically using argon or helium chambers. Machining titanium is also difficult due to its low thermal conductivity, which concentrates heat at the cutting edge, leading to rapid tool wear and potential material damage. Specialized tooling and low cutting speeds were mandatory to maintain dimensional accuracy and surface finish integrity throughout the manufacturing process.
Joining the large titanium sections required advanced techniques far beyond conventional arc welding. Lockheed utilized electron beam welding extensively, performed inside large vacuum chambers. Electron beam welding provides deep penetration and a narrow heat-affected zone, minimizing distortion and reducing the risk of contamination compared to traditional methods. This precision was essential for maintaining the aerodynamic smoothness and structural alignment of the fuselage panels. Chemical milling, or chem milling, was also employed to thin down large sheets of titanium after forming. This process uses chemical etchants to remove material uniformly, achieving precise weight reduction without introducing the stress risers associated with mechanical machining. The sheer volume of titanium required for the Blackbird program immediately exposed a critical geopolitical vulnerability. In the early 1960s, the United States' domestic production capacity for aerospace-grade titanium sponge was insufficient to meet the demands of the classified program. Furthermore, the Soviet Union controlled the vast majority of the world's high-quality titanium reserves and production facilities. Relying on open market purchases would have alerted the Soviets to the scale and nature of the project, compromising its secrecy and potentially triggering a price war that would halt production. A covert solution was necessary to secure the raw material without revealing the program's existence. The Central Intelligence Agency initiated Project Palladium, a highly classified operation designed to circumvent the supply shortage. The strategy involved establishing a network of shell corporations and foreign intermediaries across Europe and Asia. These entities placed large, seemingly unrelated orders for titanium sponge directly from Soviet suppliers. The titanium was then routed through multiple third countries, masking the ultimate destination and the true end user, Lockheed's Skunkworks. This maneuver successfully secured the necessary tonnage of raw titanium sponge, ironically using Soviet resources to build the aircraft designed specifically to evade Soviet defenses. This operation was a critical non-technical component of the SR-71 success. Raw titanium sponge, the porous product of the Kroll reduction process, is unusable for aerospace applications until it is consolidated and purified. The acquired sponge had to undergo multiple stages of vacuum arc remelting. This process involves pressing the sponge into electrodes and melting them under high vacuum conditions, often 2 or 3 times, to remove volatile impurities like magnesium chloride and ensure chemical homogeneity. The resulting titanium ingot was then forged and rolled into the specific sheets, plates, and billets required for the Blackbird components.
Maintaining purity during this conversion was paramount, as even trace contaminants could lead to catastrophic structural failure under Mach 3 stress. The novelty of working with T13V11CR3AL and the stringent performance requirements led to extremely high rejection rates during fabrication. Early estimates suggested that up to 80% of the initial titanium components failed quality control inspections due to issues like microcracking, improper heat treatment, or surface contamination. This necessitated the development of advanced non-destructive testing methods, including ultrasonic inspection and specialized dye-penetrant techniques tailored specifically for titanium alloys. The high failure rate significantly increased the overall cost and timeline of the program, forcing continuous refinement of manufacturing protocols and material handling procedures. The final assembly of the SR-71 required specialized tooling designed to handle the unique properties of titanium. Because titanium is prone to galling, standard fasteners could not be used. Specialized titanium fasteners, often silver-plated to prevent cold welding and seizing, were mandatory for all structural joints. Furthermore, the airframe was designed with intentional gaps and loose panels. These tolerances accounted for the massive thermal expansion that occurred during high-speed flight. The aircraft was structurally sound only when heated to operational temperatures, meaning it leaked fuel profusely while stationary on the ground, a necessary design compromise dictated by the material science.
The SR-71 program fundamentally advanced the field of aerospace metallurgy and fabrication technology. The necessity of overcoming the challenges posed by titanium 13V, 11Cr, 3Al led directly to innovations in electron beam welding, chemical milling, and high-vacuum processing that became standard practice in subsequent high-performance aircraft programs. The forced development of robust quality control protocols for titanium set precedents for future military and commercial aerospace standards. The successful management of the complex titanium supply chain, though covert, demonstrated the critical intersection of geopolitical strategy and material science required for achieving technological superiority in weapon systems development.